In this problem, we have 3 blocks with given weight, and they are stacked together. But block A is also supported by this cable connected to the wall. And we need to determine the minimum force P, which is applied on block B, the middle one, required to move block B, and state how the movement is. So as you can see, because block A is not going to move, therefore there are actually 2 situations. First is when block B moves by itself. So actually it's already written here. Or block B slides with C. So both of them slide together. It's not likely that any of these boxes will tip over. A clue will be you are not given any dimensions. If you need to consider tipping over, you have to have dimensions to work with. So in this case, we can neglect any other type of motion. So before we start to investigate these 2 situations, let's first draw the free body diagram of block A, because we know that block A is not going to move. So we will have block A, its own weight, 100 Newton, tension force from the cable, and normal force NAB with not specified location. And then because block B is going to move to the right, therefore the relative motion of block A with respect to B is to the left. So the impending motion of A with respect to B is to the left. And frictional force, because frictional force always occurs between 2 surfaces, therefore frictional force resists relative motion of one object with respect to the other. Therefore, in this case, the impending motion of block A, the relative impending motion of block A, is to the left with respect to B. Therefore, the frictional force is to the right. So from here, we can solve for the normal force from a simple equilibrium along the vertical direction to be 100 Newton. And because block B must slide under A, there's no other type of motion possible between A and B. Therefore, sliding will occur. When sliding is about to occur, the frictional force FAB is the maximum static friction, and that equals to mu S, which is this one right here between block A and B times normal force NAB, which equals to 0.2 times 100 Newton, which is 20 Newton. So that's the force friction from block B to block A. So with that determined, let's investigate the 2 situations. Situation 1, when block B slides by itself, and let's determine what is the minimum force P needed for that to occur. So for that to occur, again, we draw the free body diagram of B. It has 100 Newton force of its own weight. But don't forget, we have this force right here. This is the normal force from B to A. Because of action and reaction, we also have the same normal force NAB, which equals to 100 Newton. That is the force exerted by A to B. NAB is actually, we don't know its location. At this point, it's not very important because, again, we cannot write any moment equilibrium equations. And then what else? We have this force right here, that is the frictional force from block B to block A. Therefore, again, because of action and reaction, we will have the same frictional force but opposite direction. That is 20 Newton but points to the left. And then continue to draw the free body diagram. We will have the normal force from block C to block B. And because the block B is moving to the right with respect to block C, therefore the frictional force between them is to the left, because the relative motion of B with respect to C is to the right. Therefore, this frictional force is to the left. And then don't forget the force we need to solve for, which is this P force here. Let's call it P1. So now we have completed the free body diagram. So again, we can write our equilibrium equations. Resultant force along the x direction equals to P1 minus 20 minus FBC equals to 0. Resultant force along the y direction equals to MBC minus 100 minus another 100. One of them is a weight, the other one is MAB to be 0. And because sliding is going to occur between the BC surfaces as well, therefore FFBC also equals to mu S and BC, and this mu S is this one right here between the BC surfaces, that is 0.3 multiplied by MBC. So as you can see, we have now 3 equations and 3 unknowns, P1, FFBC, and MBC. So 3 forces, 3 equations, 3 unknowns, we can solve for all 3 of them. Therefore, P1 equals to 80 Newton. And now let's solve for the second situation when B slides with C. So for this second situation, we're going to draw the free body diagram of BC together. So they are now considered as one system. So we have the total weight, I'm going to put it here at the center. Total weight is 200 Newton now, sorry, not 200 Newton, but 100 plus the weight of C, which is 300. So the total weight is now 400 Newton. And then at this surface, this is the surface between A and B, we still have our NAB of 100 Newton. We still have our FAB of 20 Newton. That is the same as before. And now at this bottom, we have the NC, which is the normal force from the ground to block C. And because BC together have this impending motion to the right with respect to the ground, therefore the frictional force FC here is to the left. And then don't forget the the applied force P2 that we need to solve for. So we do the same thing. We summarize the resultant force along the x direction. That equals to P2 minus 20 minus FFC equals to 0. Resultant force along the y direction equals to normal force C minus 400 Newton total weight minus 100 equals to 0. And lastly, because sliding is going to occur at the surface between C and the ground, because BC are going to slide together, therefore FFC does equal to mu S and C, and that mu S is this 0.1 times NC. So again, 3 equations, 3 unknowns, P2, FFC, and NC. So we can solve for all 3 of them. So from here, P2 is determined to be 7 Newton. And because P2 is smaller than 80 Newton, which is P1, therefore the conclusion is it's more likely that BC will slide together. And the final answer is P equals to 7 Newton.